Hello, this is Spencer Lyon, and in this video, we will begin learning about the field of graph theory. Now, graph theory goes by another common name called network science, and it is the study of how things or entities may be connected in a network or graph. Some examples of common graphs might be the transportation graph that is highways or roads in a populated area. You can also think about electrical networks, where you have power plants and homes being connected via power line. There are also many, many other examples of graphs that we'll talk about as we continue forward. But keep in your mind that the key feature of a network or a graph is that we have some entities that can be connected. Now, we're going to be using the Python programming language as our main environment to study graphs. And so we assume at this point that you have a working Python environment set up. The goals for this particular lecture are to understand the key components that make up a graph or a network. We'll also become familiar with the Python package networkx, which is a very popular or common library used in Python that enables convenient and easy exploration of graphs and patterns within graph. We will then talk about some key metrics or computable statistics with graphs, and we'll even talk about some of the algorithms behind them. One algorithm that we will implement together is called the breadth first search algorithm that can be used for many things, including figuring out the shortest path through a graph or how far one node is from another. The key reference that we would point you to for the material contained in this lecture is Chapter 2 of a textbook by Easley and Kleinberg. And if you click the link here, you can actually get free access to this textbook, and we highly encourage you to do so. The textbook is very well written, comes with a lot of great intuitions and examples, and you'll see that some of the examples that they put forth in their textbook actually appear here in our notes. So before we get too far into the technical details, let's take a step back and think about why we might want to study graphs. As we may be aware, or as we have learned, there are many economic, cultural, political, or social interactions that are influenced by the structure of relationships. For example, consider the transmission of a virus. The people we interact with each day could be represented as different elements in a graph, and I would be connected to the element representing you if you and I maybe cross paths or in the same physical location each day. And because a virus needs to spread via close physical proximity, this type of graph that could represent when two people were in the same location, or perhaps even for how long, might be very helpful in understanding the probability of a virus transmitting from one person to another. Or on a bigger scale, if we look at the whole population, it might help us understand the total fraction of people who either are currently exposed to the virus that have not yet contracted it, or maybe people who are immune. Either way, being able to understand the structure between how two people are related in terms of do they show up at the same place at the same time would be really helpful in this context. A more economic example might be thinking about international trade patterns. Many countries produce certain goods. They may consume some of that good within the borders of their country, but perhaps they produce an excess and they would like to export that good to another country who perhaps wants to consume more than they're able to produce domestically. We could represent the trade flows from one good or one type of commodity from a country to another using a graph or network. Another example might be the spread of information. Consider a social network like Twitter or another common platform like Reddit. You might be able to represent users on that platform and their interactions with each other via a graph or network. Having this type of understanding of who is seeing posts or comments by a particular user might understand how an individual's perceptions or opinions are being influenced. And this could have great ramifications for a whole number of applications. Another way that graphs may be useful, or another domain in which we might use them, would be in political studies. We might have a graph of friendship or connections professionally, and we might be able to label each entity in that graph as being predominantly conservative or predominantly liberal in their political persuasion. And there may be certain patterns that we can understand that may give useful information if, for example, we were running a political campaign. Finally, this last bullet point I have here about human behaviors, there are a wide variety of applications that could fall under this umbrella. And basically, what we're saying here is peer pressure, either good or bad, may have an impact on decision making or behaviors. And so, if we had an understanding of what who my peers are or who my children's peers are, that may give us some insight into why they have certain preferences for sports, clothing, music, etc. And it can continue to go on. A common theme here, and I would even submit that we could delete this word social, is that behaviors and outcomes can be impacted by the structure of a network. This is becoming more and more prevalent today in our hyper-connected digital society, where the idea of a person being an influencer, having a strong following on social media, can actually be very valuable to, say, a company trying to sell a product. If they get an endorsement from particular individuals called influencers, that may increase their sales or allow them to reach a broader market. Another case, and this is kind of related to the political angle, and another case where behaviors may be impacted by networks is with the creation of what are called echo chambers. The idea behind an echo chamber is that you might have some subset of individuals who share their opinions or thoughts on often very charged political issues. And the people who are most likely to view, comment, share, etc., these views are either going to be those who tend to align themselves with the beliefs of the original opinion or those who are opposed to it. And what happens often over time is that groups of people who tend to have the same beliefs or thoughts and like to share and talk about those opinions tend to find themselves in similar corner or in certain corners of networks or social media. And so what you end up with is a large group of people who all share the same thoughts or ideas, and they don't have a lot of differing or dissenting opinions going on because this environment is so aligned in their thinking, it becomes almost what's called an echo chamber. One person will say something, and then all the feedback they see about their post or their comment is in support of it. because their audience is people who share their belief. And this may lead to incorrect perceptions on how common certain beliefs actually are. And so, understanding these kind of information or social networks can really shed light on what these echo chambers are. Okay, so now let's dive in and talk a bit more concretely about what a graph is or a network is. As we've mentioned, a graph specifies relationships between some collection of items or entities. Each item in a graph is called a node, and then each relationship in the graph is called an edge. And the way the graphs are often viewed would be something like this. Over here on the left, we have four nodes labeled A, B, C, D. And then we have four lines. We have one line connecting A to B, another connecting B to D, B to C, and finally C to B. Now notice that these are just circles and lines without any arrowheads. And this is what's called an undirected graph. Typically, when we say the word graph, we mean undirected graph, but there is a special type of graph called a directed graph. Here we have the same four nodes, and there are edges between the same pair of nodes in each case, but this time there's an arrow saying A points to B points to C to D, and then D back to B. And this type of graph is called a directed graph. And this might be used, for example, if you're trying to construct a graph of social media platform and understanding if one user follows another. With that domain in mind, we might say that the arrow points from A to B if A follows B. So in this case, A would follow B would follow C follows D, and D follows B. But in this case, there's actually no mutual following. Nobody follows each other. The undirected graph over here on the left might be useful for a setting where you want to understand if people took the same class in college. So each node here represents an individual, and there is an edge between, say, person A and person B if they ever took the same class in college. You'll see here that person B in this example would have taken a class with C and with B and with A. And because of this triangle structure here, we might assume that persons B, C, and D were all in the same class at the same time because they were connected. D is connected to both B and C. And likewise, there's a mutual connection between C and all of its neighbors. What would also be true, because C and A were never in the same class, there's no edge there, B must have taken a second course in which A was present, but C and D did not participate. And there are many other examples that we could apply to this same structure. So, as we've learned, a large part of doing data analytics and data work is figuring out how to take some phenomenon or an understanding from the world and represent it numerically so that we can do computations with it. Graph theory is no different. So we might ask ourselves, given this graphical representation of a network, what might we do to represent that same network numerically? One very common approach is to use a matrix or two-dimensional array that's filled with 0 or 1, and this matrix would be called the adjacency matrix. Suppose we have a graph with capital N nodes, and without loss of generality, we'll just call them the integers 1, 2, 3, all the way through n. Previously, we were talking about nodes labeled A, B, C, D. Now we would call these 1, 2, 3, 4. Then we will have a matrix A where each element is drawn from this set 0, 1, and the matrix will be n by n. Now, element ij, so this represents row I, column j, will be 0 unless there is an edge between nodes I and node j. By default, when we consider most typical graphs like this one, we will say that the diagonal, so element jj, will be 0. Now that would be, what would that represent if that were a 1? That would represent B having an edge that points back to itself. For now, we're not going to allow that. It is possible to create graphs of that structure, but at least for right now, we're going to disallow that. So each edge has to go between two distinct nodes. And the implication there is that the diagonal is always 0. So let's think through how we would represent our graph from above using an adjacency matrix. We had 4 nodes. We're going to map A into node 1, B is node 2, C is 3, and D is 4. And then we had the following structure of nodes. A was connected to B, and then B to C, B to D, and C to D. Now, the adjacency matrix for this example is the following. We have here zeros along the diagonal, as we mentioned just a moment ago. And then we want to represent the edge between elements 1 and 2 by putting a 1 in this position. Now, because we're considering an undirected graph, we would also have a 1 in 2, 1. And so what this represents is this part of the graph where we have node A and node B connected. The fact that these are both set to 1 says A is connected to B, and, so that's this one, and then B is also connected to A, which would be this element right here. Then, if we wanted to think about this connection from B to C, we would go to row 2, column 3, row 2, column 3 is right here. And again, because we're undirected, we will have a symmetric component at row 3, column 2. So these two elements represent this edge. We may also think about the edge from B to D, which would be the 2, 4 element, or the 4 or 2, excuse me, element in our matrix. And then finally, we have one more edge, which is the 3, 4 edge that connects C and D. So that would be this element here and this one, because we have row 3, column 4, and the symmetric version. So this is the adjacency matrix for the undirected graph we had on the previous slide. Let's now think about how we could represent that adjacency matrix in Python. So what we'll do first is we will import the NumPy library that we've come to use when we need to analyze multidimensional arrays. And then we'll type in the corresponding matrix here. So you can trust that we've done this properly. If you look here at the more formatted printout, we see here that exact same graph we had before. We've got ones here representing the edge from 1 to 2. Right here's the edge from 2 to 3. Here's the edge from 2 to 4. And finally, the edge from 3 to 4. Now, if you're handed an adjacency matrix, what would you then do with it? So you could actually extract a lot of information about the structure of that network using the adjacency matrix. For example, you could compute the total number of nodes in the matrix or in the graph by looking at the number of rows or columns in that matrix A. You could also compute the total number of edges in the in the graph, by summing up the elements in A. And we'll make the slight adjustment here that for the undirected graph we had before, we'd actually have to divide that by 2 so we don't double count that symmetric connection. We could think about which node has the most edges. And the way we would do that is we would look kind of one row at a time. So we're going to do this argmax over I here. And then we'll just sum up row I. We'll compute the sum across columns J of Aij, and whichever row has the most elements with the number 1 in it would be the node with the most edges. So in our example before, we had 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0. So in this case, if we were to sum up each row, we would get that the first node had 1 connection. Second node, B, in our example, has 3. C has 2 connections, and D has 2 connections. So in this case, we would say that kind of the maximizing, the argmax in terms of which row would be the second row. We could also compute the average number of edges per node. And here what this would be is we could sum up the total number of edges. Here what we would do to compute the average number of edges is we would have that factor of 1/2 that we remembered over here. We'd pull that out front, and we'd also divide by an n, and then we just multiply this kind of scaling term by the sum of all the elements in A. So without the n, if we just looked at this part, this would be the total number of edges, and then we simply divide by n to get the average number of edges per node. Let's practice this a little bit. So in the code cell below, we have defined for you an adjacency matrix called A underscore EX1, representing A exercise 1. Now, using this matrix, we would ask you to compute the following numbers. We would like for you to compute how many nodes are in the graph, how many edges are in the graph. Let's find the node with the most edges, the average number of edges per node, and then, so these 4 we talked about before, and we have one additional request that you find the number of connections for some arbitrary node. Here we ask for node 7. And so we have here a function that will create a random adjacency matrix, and then we've defined that A exercise 1 here for you. And what you should do at this point is pause the video for a few minutes, look through these questions, and see if you can answer them taking this matrix as your adjacency matrix. We won't be working through this particular solution together, so do your best, and when you've given it a good effort here, you can then unpause the video and resume. Okay, now let's start to talk about the Network X Python library. As it turns out, as most things, Python has really strong support for working with graphs and network. There are a handful of well-used packages for doing network science. However, uh, perhaps the easiest to get started with, and the one that you'll find the most online help or resources for, is called NetworkX. And although it's easy to use, it doesn't mean it's not extremely powerful. We'll see a little bit of its power here. We work through exercises. So what we'll do is we'll first import the network X library, and we'll give it an alias NX, which is kind of the conventional import. And then we'll use that adjacency matrix A that we had before. If you remember what A looks like, this was that uh, adjacency matrix for the ABCD graph we had depicted visually. So all we need to do at this point is we say, okay, network X, there's a convert matrix subpackager library for working with adjacency matrices. And we will call the from NumPy array method, passing in our array A. When we do this, we get back a graph, and we can check the type of this. And we'll see here that this is a network X graph. And there are a few common properties we can immediately start looking at. For example, the edges property will return to us something called an edge view. This tells us that there is an edge between nodes 0 and 1, nodes 1 and 2, 1 and 3, as well as 2 and 3. So this is that integer representation we had before, but because this is Python, they started counting at 0 instead of 1. So you'll see these same numbers in the previous slides, just incremented by 1. We can also ask it for what the nodes are. And here it tells us that the nodes are labeled 0, 1, 2, 3. So node 1 in this instance corresponds to any time you see a 1 up above in the edge view. We'll see examples when they aren't just the default integers here pretty soon. Once we have a graph in the Network X library, we can actually use it to help visualize our graph. One thing we'll point out before we show this is that the actual placement of the nodes is totally random. And what happens under the hood when you ask Network X to construct a graph, or sorry, a plot of our graph, it will first assign a random position to every node in our graph, and then it will move them around a little bit, kind of jiggle the positions from their initial random conditions so that all nodes are clearly visible and the edges are also somewhat equally spaced. It's a little bit loose the way I'm describing it, but the idea is they're going to construct randomly placed nodes in such a way that the output is maximally uh, visible or interpretable to people like us. The most important thing to know about this type of plot is that the placement or position within the canvas is not important. What is important is the structure, which nodes are connected to other nodes. So when we draw this here, we see that they've basically kind of flipped our previous graph, at least how I drew it before, upside down. So before we had this kind of structure, and they've basically flipped it. So these two nodes are the same, these two, these ones, and these ones. But we can see here, in terms of structure, this is equivalent. So here we have that node B that's connected to C, D, and A, and all the same edges are still represented. We'll pause a little bit and think about one technical detail. So when we have a relatively small graph or network to look at or to work with, how we've represented things so far using our adjacency matrix is completely fine. Using this two-dimensional array of floats or integers is not a problem when the graph is small. However, as the size of the graph grows in terms of number of nodes and edges, the way we think about storing our graph or representing it to the computer can matter a great deal. So consider a graph or network of Facebook. And we want to say that each node is a Facebook user, which there will be over 1 billion nodes according to Facebook. And each edge, an edge would exist between two nodes if those people have ever directly interacted, either by commenting on a particular post, or maybe liking a post or sharing one. That would constitute a connection between those two parties. Now, that thinking about the billions of nodes out there and any possible interaction, we've now got multiple billions of possible edges. And so trying to represent that, you can start to see why thinking about being particular or deliberate about the network structure to the computer may start to matter. So to dive in a little bit further on the details, to store our 4-node, 4-edge graph, we used a 4x4 matrix of 64-bit integers. So we have here 16 elements, each with 64 bits. This ends up being 128 bytes. So 1 byte in computer memory or storage units is equal to 8 bits. So if you multiply 16 by 64 and then divide by 8, you get the answer of 128. Here I proposed another example where each node is a particular website, and there's a connection from one node to the next. If there is a link pointing from one site to the other. Here again, we're going to have potentially tens or hundreds of millions of nodes and edges. And so if we have something that's 10 million by 10 million, and then multiply that by 64, we're going to be talking probably in the petabyte or exabyte range of storage. Now, there are a few ways we could be a bit more efficient here. One of the easiest or most obvious would be to only store the upper triangle of the matrix. So if you remember, we had our matrix here that was 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0. So this is a symmetric matrix, and the diagonal is 0. So we stored all 16 of these integers. However, we could have, without losing any information, stored only the upper triangle, which would be this section in blue. So now instead of storing 16 integers, we only have to store 6 integers. So this, very valid, and it would definitely work. Another very valid and fairly easy to implement idea would be to store, instead of a 64-bit integer, store just 1 bit. All we have to represent here is either a 0 or a 1. That's exactly what a bit is. It can take on the values exactly 0 or 1. So we could just store this using a Boolean array or an array of bits. Here we would then reduce the size of our matrix by a factor of 64. Another valid approach would be to use a sparse matrix. And here what you would do is, instead of storing the whole matrix like we've done here, you would instead store I and then j. You would store a list of ij's only for the ij's that are non-zero. So whether this is more or less than 6, like we have here, would depend on how many edges there are in your graph. If you had only 2 edges, then this would make you store 4 numbers. But if you had, in this example, 4 edges, you'd end up storing 8. So which one you would choose between these two, it depends on edges. Depends on the number of edges. Finally, another option would be to store a list of edges. And this is very similar to what we saw up above, where Network X showed us that edge view item. So let's just show you one example of another way we could think about that edge view. Here we have a dictionary where we have as keys each node in our network, so 0, 1, 2, 3. And then we have as the value a list of integers representing which other node that one's connected to. So here we could say node 0 is connected to only node 1. Node 1 is connected to nodes 0, 2, and 3, and so on. And if we ask Network X to show us the adjacency matrix or adjacency view, this is really similar to what they're doing. So notice here they have what looks like a dictionary where the keys are the names of the nodes. So here this is key 0. Now the value, instead of just being a list of integers, a little bit more general than that. They allow you to represent different strength of connection between nodes. Now, we haven't learned about that yet. We will in a future lecture. But for now, what we'll take away here is that as the size of our graphs or networks grows, we need to be a bit more deliberate in how we think about storing them. And so these are all possible ways that we might be more efficient in storing them rather than using that whole matrix. We'll now turn to studying some of the concepts that are useful and come up when we're trying to analyze or gain information from a graph. Now, one very natural question that can often arise when you're presented with a graph, especially when you see the visual representation of a graph, is how you might move things from one node to another, how things might flow through or on the graph. For example, when we talk about things, we might mean how information spreads between a group of friends. We might be talking about how data travels along the internet. Maybe we're studying how diseases can be transmitted from one person to another, or even how people navigate a subway system to reach a particular destination. In each of these examples, the flow of things, which again, the actual version of things depends on the context and the domain. In each example, though, these things are flowing from one node to another, but always across edges that exist between that pair of nodes. When we consider the flow of something from one node to any other node, either a direct connection or one that you have to make a few stops, this type of flow from one node to another is called a path. So let's consider an example. Below here, we have a map of the continental United States, and overlaid on top of this is a graph or network of something known as ARPANET. Now, this was developed before the days of the modern internet, and in some ways can be thought of as a precursor to the internet. Here we have a number of respected research or academic institutions that often collaborated and they needed a way to send and share data or other research objects between one another. So each of these locations had developed their own kind of in house computer system that their faculty or employees could use. But in order to collaborate, they needed to do so in a physical way at the time, be it storing data on some sort of physical medium, like what we would think of as a flash drive today, and then shipping or somehow physically delivering that physical hardware to another location. So they developed what's called the ARPANET, which enabled the electronic transfer of data and research materials amongst these institutions. And we'll see here that This network is composed of, let's count, 13 different nodes. And there are certain patterns that exist that we'll talk about. When we're thinking about paths, though, suppose somebody at UCLA over here was collaborating with somebody at Harvard. Now, what they might do in order to send their data to their collaborators at Harvard, they might have to go on a path through the network, such as this red one. So UCLA to RAND to BBN to Harvard. Another possible path could be for them to go to Stanford, SRI, Utah, MIT, BBN, and Harvard. And so there are a number of different paths that you could take through this network that can connect UCLA with Harvard. There's some different properties, though, that we'll study about which path may be most effective, which paths are crucial or most important in some way. And so those are questions we want to be thinking about. Maybe how many steps does it take along this green path compared to the red one in order for the data to be successfully moved from UCLA to Harvard? So, in order to study this a bit more, let's actually define the network using network X so that we can access it from Python. And the way we'll do this is we'll construct a dictionary that we call nodes, where the keys of the nodes are the name, or the keys of this dictionary are the names of the nodes, and then the associated value is each of the other nodes connected to the key. So in this example, suppose we consider Utah. This description, this entry in the dictionary would say that Utah has a direct connection to SRI, SDC, and MIT. So if we go back, we can see Utah right here does have a direct connection to SRI, as well as SDC, and to MIT. And we could go through and double check each of these entries in our dictionary. But for now, you can trust us that we've entered these correctly and that each key maps to all of the connecting nodes. So we'll go ahead and define this dictionary, and then we can pass it directly to the graph constructor for the network X graph. So now we have this object ARPA is the network X representation of the ARPANET. We'll go ahead and use the network X tools to visualize this. And we see here that we have the same structure. Now, things aren't placed at exactly the same location. For example, in this particular example, Utah ended up being a little bit lower than UCLA and about the same height as MIT, which, if we think about the geography of the United States, Utah would not be further south than UCLA or exactly even with MIT. But as we've learned previously, when we're visualizing a graph like this, the important part is not exactly where the nodes are placed, but rather their structure. And so the key feature here that is being represented is that Utah is connected to SRI, SDC, and MIT. So, one important concept that will be useful for us when we analyze graphs is the concept of a cycle. A cycle is defined as a path that starts and ends at the same node. In our ARPANET example, one cycle might be link, case, tarn, arv, BBN, MIT, back to link. So, one question we might want to ask is what's the shortest possible cycle in a graph, including all the endpoints? So, if you were to think about and maybe just stare at this for a few minutes, what would be the shortest possible length or the least number of edges traversed to complete a cycle? You could think about that for a minute. Maybe pause the video. While you do, we'll go ahead and talk about it now. So if we had these 2 points, so suppose we wanted to create a cycle that started and ended at UCLA. We have to traverse one edge to leave UCLA, and then we could go right back. So that would be, as if we were trying to write down the nodes, it would be UCLA, UCSB, UCLA. So that would be including 3 nodes, and it would traverse 2 edges. If you made the additional rule that you're not allowed to, quote, backtrack or travel the same edge multiple times, then you would have to do something like UCLA, UCSB, and then traverse this one to SRI, and then back to UCLA. So in this case, we traversed 1, 2, 3 edges, and there were a total of 4 nodes that we would use to describe the path: UCLA, UCSB, SRI, UCLA. So when we talk about the length of a path, really what we mean is how many kind of dashes would we have to write in order to describe the whole path. So in this particular cycle, it has length 1, 2, 3, 4, 5, 6. Now, network X can tell us if a graph is what's known as connected. We'll talk about this definition of connected. So a connected graph means that each node in the graph is reachable via some path from every other node in the graph. So consider this graph right here and think about that definition. A graph is connected if every node is reachable via some path from every other node. In this case, the ARPANET is a connected graph. No matter where I start, I can always find some path to any other node in the graph. If, for example, we added another institution that did not have a connection to the ARPANET, for example, suppose we consider NYU's computer system kind of in isolation. If we were to add this node to the graph, but not any edges to an existing node, this would now become unconnected because we have a node here, NYU, that's not reachable by any of these other nodes in the graph. So this network is connected. If we added another node, and maybe we added a node that was connected like this would be constructed of this one big graph is now not connected, even though it has 2 kind of connected subcomponents. And we'll talk about that more later on. But network X can tell us very quickly and easily if a particular graph is connected. So here we see that the ARPANET graph or network is connected. Now, it's very natural to assume or think that many real world networks are connected. For example, a transportation network like the subway system in a major city. This, kind of to be useful, needs to be connected. It needs to be possible to reach any destination, any subway station from any other station. You might have to make a few transfers or make a large number of stops, but in order to be a useful network, it needs to all be connected. Another example of a network that just makes sense to be connected would be the internet. Now, when I say the internet, I really mean the system of computers and internet kind of transmission lines that make up the hardware side of the internet, not necessarily the content or digital side, where we think that every website has to be reachable through clicking links to every other website. I would argue that the content type of internet network would be not connected, whereas the hardware part of the internet network likely is connected, so that when I'm on my computer and I connect to the internet, I'm able to make requests to load arbitrary websites. There's Unless there's some sort of digital firewall preventing me from loading a website, the internet is useful to me because no matter where I am, as long as I can connect to the internet, I can access all of my favorite and important websites. So these are examples where having a connected network makes a lot of sense, but it's entirely possible to have a not connected network. For example, consider social networks, where the nodes are people and the edges represent friendships. It's very possible that if you consider college students from different universities or even universities in different countries, it's possible that there are no connections between any of the students at University 1 with any of the students at University 2. In that case, you would consider the network of college students to be disconnected. Another one you might consider, suppose you're studying the supply chain network, and you include only a couple industries: the textile industry for clothing, as well as microchip manufacturers or suppliers for the technology industry. It's very possible that the suppliers of textile companies are a completely different set of entities or nodes than those that supply components for a microchip. And in this case, you might think that there are no connections between suppliers of textile components and suppliers of microchip components. Now let's formalize a bit more that notion of distance or how long a particular path is. We'll define the length of a path as the number of steps that it takes from beginning of the path to the end of the path. For example, there could be a path through our ARPANET that goes from MIT to BBN to RAND to UCLA. Now, this path has a length 3 because there are 3 edges represented here by the dashes that need to be traversed in order to go from MIT to UCLA. This is what we call the length of a path. Now, the distance between any two nodes in our network is the length of the shortest path between those nodes. So, for example, with ARPA, you could consider uh, paths between MIT and UCLA, where one might be UCLA, RAND, BBN, MIT, where we traverse 3 edges. Or you can consider another one that goes UCSB, SRI, Utah, SDC, RAND, BBN, MIT. And in this case, there would be 1, 2, 3, 4, 5, 6 edges that connect UCLA to MIT. Both are valid paths, and we can compute the length of each path, but the distance between UCLA is 3. We could either go up to RAND and then BBN, MIT for a length 3 path, or in this case, we could actually go down to SRI, over to Utah, and then to MIT, again for length 3. But there are no shorter paths that have less than 3 edges that connect UCLA and MIT. So we would say that the distance between these nodes is equal to 3. Network X can compute distances for all the nodes in our graph using the shortest path length function. As an example, we will ask Network X to study our ARPA network and compute the distance between UCLA and every other node in the graph. And here it returns to us a dictionary containing all of the node names in the graph and then the distance between UCLA and that node. We'll see here that UCLA is at distance 0 from itself. We don't have to traverse any edges to arrive at UCLA when we start from UCLA. all of its direct connections or nodes to which it has a path or an edge are at distance 1. We only need to traverse the kind of dedicated connection between UCLA and each of these 4 nodes in order to arrive there. There are a handful that are then reachable by crossing an additional path or additional edge, and these would be at distance 2. There are a couple more at distance 3 and distance 4, and finally, Case here is the furthest node from UCLA at a distance of 5. So suppose that you are asked how you would go about computing the distance between, for example, Harvard and any other node. You can't just call into the shortest path length function. You actually have to write the algorithm. How might you do it? Well, one way you could consider this would be an iterative approach where you start with Harvard and note that it is at a distance 0 to Harvard. Then you would move on to the nodes directly connected to Harvard and note that these are all at a distance 1. Then, starting from each of these distance 1 nodes, you would consider all the nodes that are connected to them. And you'd have to make sure not to double count anything. But any new nodes you find, by saying, let's go from Harvard 1 step away, and then from each of these neighbors, go an additional step. Any new nodes you come across would be at distance 2. And then you consider all the nodes that are 1 step away from these distance 2 nodes, and you'd say that they're distance 3, and so on. And you continue just exploring edges 1 layer deeper until all the nodes have been visited. Now, this algorithm or approach right here is well known, and it's actually called the breadth first search algorithm. And the reason for that is if you have a network, suppose you have a network where you want to start from some node and then consider all of the possible distances. One way to do it, if you wanted to find the distance between, say, the starting node up here and this node, one way to do it would be okay, let's just go directly there and see how far the distance is. This would be called a depth first search because I'm going deep along a particular path before I consider alternative paths. This is not what we're doing in our example. We're doing breadth first search, where we say, okay, let's first go wide. Let's consider all of the immediate neighbors in step 0. Then let's go 1 step deeper and consider all of the connections of those neighbors. So this would be the step 0, or this would be the step 1. This would be the set of step 2. And then finally, we end here with a step 3. And so the breadth first search algorithm first considers all possible starting decisions and then all possible second decisions before going deeper into the network. So let's look back at our ARPANET example and consider a breadth first search starting at MIT. Here's how it would work. We first begin with MIT, and as we mentioned above, we will note that MIT is at a distance 0 from itself. Then we consider all of the nodes that are directly connected to MIT, which include Utah, BBN, and Link, and we'll note that these are all at a distance 1. We'll then go and consider all of the nodes that are connected to Utah, all the ones that are connected to BBN, and all the ones that are connected to Link. And we'll end up with this set of 5 nodes that are at a distance 2 from MIT. Then we dive down 1 layer deeper. We look at all of SRI's new connections. STC doesn't give us any new connections. It's connected only to Rand and Utah, which we've already accounted for. Harvard and Case are both only connected. The only new node they're connected to is Carnegie Mellon. So after doing that, we notice that SRI gives us all the new nodes, and these are at distance 3. And if we count these up, we will realize that we've now accounted for all of the nodes in the network. So MIT is at a maximum distance 3 from every other node in the network. Now we want you to work through an exercise. And we'll warn you, this one is a bit difficult. So you may want to pause the video for a little while, do your best to spend some time thinking it through. Uh, and the goal for this exercise is for you to code up the breadth first search algorithm to compute the distance from any given node to all other nodes in the graph. What we want this function to return is a list of lists of node names. So for example, the return value for that MIT example we just came up with would be that we have the first element would only include MIT. This would be the element 0 of our outer list, and this represents all nodes at distance 0. Then we would have Utah, BBN, and link in this next element, and these are all the nodes at a distance 1. We would then include these 5 nodes that were at distance 2, and finally we have one other element in this where we have those last 3 nodes at a distance 3. So the idea is this outer list just contains the elements of it are collections of nodes, and then each of these collections are the list of nodes at that particular distance from the starting point. So what we would like for you to do is to be able to fill in the function below for how to implement this algorithm. And we'll work on providing you, when we give you the notebook, we'll give you a little bit more detail here on exactly what that should look like. So go ahead and pause the video and do your best to solve for what the breadth first distances algorithm might look like. And when you're finished, you can return here where we will actually go through and code it up. Okay, so if I were to work on this problem, the first thing I would do is I would need to consider that I have to keep track of all the nodes that I've already visited. So here I'm going to create what's called a Python set using these curly braces, and I'm only going to include the start node so far. A set is a special data type in Python that's kind of like a list or a tuple, but it can only keep one copy of every element. It only keeps unique elements. So I'll start there, and then I will note that my starting nodes is only this kind of start node. And we'll keep track. I'll show you what this variable is going to do here in just a minute. And I'll also say that we want to start. The output should only have this list here, this inner one, containing start. So these are all of the nodes at distance 0 from the starting node. Okay, so then what I'm going to do is I'm going to say while the length of visited is not equal to the length of g.nodes, no, I haven't found everything. I need to keep working. Then I'll say, okay, my new nodes, I'm going to just create an empty list that I'll add on to. And I will start to consider all of the neighbors of these nodes. So I'll say for node in starting nodes, for neighbor in graph.neighbors, node, if neighbor not in visited, and what I'm going to do, there's two things I need to do. So here's how where we are so far in the algorithm. All of the nodes that I've already seen, but I need to consider their connections. Let's go ahead and look at all of the neighboring nodes to that particular node. So g.neighbors will return to me a list of names for nodes that are directly connected to this argument node. So neighbor will be a different node that has a connection to this node. Then I'll say if this neighbor has not yet been visited, if we haven't seen this one yet, what we should do is we should say visited.add node or neighbor. And then we should also say that new nodes includes this neighbor. When we're done considering all the starting nodes, we'll then say that the next element in our final output should be that list of new nodes we found. And the starting nodes for next iteration should be only these new nodes that we found. All right, so we're going to let this thing run. And given that it is still running, that's a strong sign that I made a mistake. So I'm going to go ahead and break out of this recording and we'll come right back and I'll fix my mistake. I have to cancel this execution. All right, thanks for bearing with me. I did find my typo. So my typo here is right here. I had an extra S and I said startings nodes instead of starting nodes. And so now what I'll do is I will redefine my function and we'll execute it for MIT. Oh, left some debugging code in here. Execute it for MIT, and now we'll get the answer we were expecting. The first item in the outer list is a list containing only MIT, representing that MIT is the only node at distance 0 from itself. At the 1 position, we have all the nodes at distance 1 from MIT. Here at the 2 position are the distance 2 nodes, and finally we have the distance 3 node. So let's think back through what this algorithm actually did. We'll start at the very beginning. We first initialized out as being a list where the only element is a list containing MIT. So up until this point, we have just the MIT right here. So this line of code gave us this part of the output. Then we just kind of kept track of where we visited so far, as well as what nodes we should be exploring. And now we'll say, while we're not finished yet, while we haven't seen everything, let's go ahead and create a fresh set of brand new nodes that we're seeing for the first time. Then, for each of the nodes that we're currently considering, or in other words, each of the nodes at the last element of out so far, let's go ahead and look at all of that node's neighbors. So let's go ahead and look at all the nodes that are directly connected to the starting node. Here, this would give us Utah, BBN, and Leak. We'll have to double check that we haven't already seen that node somewhere up above. And as long as that check passes, we'll go ahead and we'll mark that overall we've seen that node, and we'll add it to this new nodes list of items we're coming across for the first time. Now, this list of new nodes we're seeing for the first time becomes the next element of our output. And so at this point, we will add the second list right here to our output. Then, before we begin the next iteration, what we have to do is say, okay, I'm done examining MIT and all of its connections. And remember, that's what starting nodes was to begin with. I'm done with MIT. Now I need to consider all of the nodes that are connected to any of these guys. So I'm going to say starting nodes is again equal to that list of new nodes. So now when I get back up, I have a fresh set of new nodes that I'm about to discover, but I can go ahead and iterate over Utah, consider all of its connections, BBN, consider all of its connections, and Lincoln, and consider all of its connections. As long as I haven't seen them, I'm going to add them to the overall counter, as well as this new element, and I'll include them at list 2, or distance 2. And then I'll repeat the process for SRI, SDC, RAND, HARV, and CASE. If I consider all of their neighbors, I end up discovering for the first time these 4 nodes at the bottom. And at this time, when I get back to checking, is the length of my set noting what I visited different from the number of nodes? I'll get false. Because after I've considered these 4 nodes, I will have seen all the nodes in my network. And at that time, we can break out of this loop. We'll return out, and this is what we end up with. So it was instructive for me to be able to consider how I might code up this algorithm, but we actually don't have to do things like that by hand all of the time. As you may have guessed from our experience with other Python libraries, NetworkX comes with a lot of helpful features built in. One of these is an algorithm in the networkx.breadth first search subpackage called BFS tree. So let's see what would happen if we call this method using our ARPANET and the BBN node as the starting node. What we'll get back is an instance of what's known as a digraph. Digraph is the network X data type for a directed graph. We can also ask this digraph, we can ask it for the length of the number of nodes. So here it says there are 13 nodes. And we can ask it for the length of its edge list, which would give us 12. So we have now a 13 node, 12 edge directed graph. So far as we've been talking about the ARPANET, we were considering an undirected graph where all that was relevant for us to represent was whether or not 2 nodes were connected. Now the directed graph takes one step further, and not only do we consider are 2 nodes connected via an edge, but we want to understand the direction of that connection. We can now be a bit more precise and say that things, whatever the domain is for our network, flow across from one node to another, across an edge in a specific direction. Now the question is, the graph we gave it, that ARPA graph, it was undirected. So why would network X, their breadth first search routine, give us a directed graph instead of the undirected one we started with? Well, to understand that, let's try to visualize it and see why. When we visualize this particular graph, there's a few things we should know. One is that if we look at BBN, which was our starting node, there are no arrows pointing into BBN. So we consider BBN to be at the top, or the kind of beginning node of our directed graph. And then all of the edges it has have arrows pointing from BBN to a different node. Then, if we consider after, say, we traverse this node from BBN to MIT, we would then say, okay, once we're at MIT, where can we reach now that we couldn't before? And in this case, we have Utah, Link, and Case. Or if we said, now let's go to RAND and see what new nodes are, we can go to either SDG or UCLA. So in each case, the arrows are always flowing away from BBN. And what this is really representing is the shortest path from BBN to every other node. And it will tell us, if we just follow the arrows, it will tell us the shortest possible way to get from BBN to any other node. Let's consider Stanford. In order to get to Stanford, there's only one possible path in this directed graph that leads to Stanford. It is RAND, UCLA, Stanford. If we look back at the full ARPANET and we wanted to go from BBN to Stanford, we'll see, starting over here at BBN, there are many different paths that get us there. We could go RAND, UCLA, Stanford, like we just talked about. But we could also go MIT, Utah, SRI, Stanford, or RAND, UCLA, UCSB, SRI, Stanford. So there are many paths in the original undirected graph going from BBN to Stanford. But this particular directed graph is telling us, if you want to get there the shortest way possible, this is the best route to take. The same would be true for any other node. Here, we want to consider BBN to Utah. We just follow the edges that lead to Utah. Another way to do it would be to work backwards. So if you wanted to consider how to get to UCSB, all you have to do is go backwards on the arrow. You go UCSB, UCLA, and then that goes to RAND, and then RAND goes back to BBN. So this is the path you'd get to go to UCSB. So let's repeat a little bit of our exercise and try to understand how we can maybe pull information out of the directed graph that network X gives us. So if you go and you use that the breadth first search BBN object, and you ask it for the adjacency representation, what it will do is it will give you a dictionary that describes the adjacency pattern in the graph. So each of the keys of this adjacency object, let's go ahead and take a look at it. Each of the keys here is going to be a node label. So here we have BBN, and then RAND, MIT, and so on. And then each of the values of the dictionary describe nodes that are pointed at by the key. So here we go. We start with BBN. We'll say, okay, let's consider that next we go to RAND, and then MIT, and then Harvard. So these are the first layer connections. And what we'd want to do to find all of the distance to is we say, okay, let's go to RAND. Let's find its element here. And it will say that from RAND, the new nodes we can reach include UCLA, and SDC. From MIT, the new nodes we can reach include Utah and Link. From Harvard, the new nodes we can reach include only Carnegie Mellon. As we get further on into this graph, we'll notice that, say, for example, from Stanford, there are no new nodes we can find. When we consider starting at BBN, once we get to Stanford, it doesn't give us any new nodes. So this is an empty dictionary. So right here, what we have is we have a function BFS tree distances that takes in a directed graph this time, which we'll assume you obtained using the breadth first distances function. And it has a starting node. And what your task is to implement the body or the logic of this function so that the return value has the exact same shape as the function we wrote up above. So we want it to return to us this list of lists. We got to go from that many dictionary version Network X gave us to this list of node names. And that's the task that we asked for you to do here in this function. Go ahead and pause the video. You can try to work through this, but we'll go ahead and we'll continue on do this ourselves. So here we go. If I were to do this function, let's see if we can do it without an error this time. I would first say start is the initial return value. And I would say to visit, just start. And while we still have nodes that we should be visiting, let's go ahead and we'll say new nodes is this list, and for node in to visit, we want to grab our new nodes list and we want to extend that with all of the nodes that can be reached through our adjacency object from the node we're currently visiting. If we found something, we're going to go ahead and append that to the output. And then we'll say, okay, now we just need to visit on the next iteration our new nodes. Let's see if we got it right this time. Oh no. Oops, there's a typo here. New nodes. That's not good. Okay, so not quite. We missed out on something here. I'm going to go ahead and pause this for just a minute while I think through what happened, and then we'll return and we'll figure this out. Okay. One error is that after we've seen all of the nodes we're currently visiting and we've extended our list to include its connections, if we found anything, instead of putting it to visit, we actually need to put this onto our output. So now we've considered all of the next distance nodes, and that actually fixed it for me. So before, what I was doing was saying we needed to visit all of the new nodes, but that would make us cycle around over and over. So now what we'll do is we'll actually append this to our output, and just note that we only have to consider visiting the new nodes. And once we've done that, we get back a list of lists. And to check that it's the same, I'll just go ahead and put MIT back in here. In order to check this, we actually need to go back and we need to ask Network X to first compute that breadth first search object, starting from MIT. Oops. I am full of typos today. Maybe this makes you feel a little more confident in your own programming, because this is how it is for me every time. Okay, here we go. So now we can check that this routine, the one we just barely wrote, BFS tree distances, it should match the routine that we did earlier, which allowed us to compute just the breadth first distances from our ARPANET starting at MIT. So notice the difference in the input, this first argument here. We need to get that directed graph where Network X gives us that directed graph starting at MIT and traversing down. And in this case, we just start directly with the ARPA example. So when we run both of these routines, we get back the same set of nodes at each level. So now we've completed the exercise. Now we'll turn to one more component of a network, or one more key feature of a network, which is actually called a component. So a component of a graph is a self-contained subset of the nodes. And more precisely, we could say that a set of nodes is a component if two things hold. One, every node in the subset has a path to every other node in the subset. In other words, each collection of nodes we're considering as a component has to be fully connected. Second, this particular subset we're considering, it can't be part of any larger subset that also is connected. So let's see an example here. The nodes A, B form a component because starting from either A or B, there is a path that connects to the other. That's condition number one. And the second condition for this to be a component is that neither A nor B is part of any larger collection of nodes that is also connected. So here, if we were to throw in any additional nodes, it would now be unconnected. And so AB is a component. We could do the same argument for the set of nodes here, C, E, and D. Starting from any of these, we can reach any other, meaning it's connected. But if we included any other node over here, it would no longer be connected. So this satisfies both parts 1 and 2 of this definition of a component. And then here we have a third component that includes all these other nodes, F through M. Now, one example here, within this particular component, we have a number of collections of nodes that satisfy property 1. For example, consider FGHJ. These nodes are connected to one another, so they satisfy part 1, just considering only these 4 nodes. However, there are additional nodes in the graph we could add, and it still remains connected. So this violates the part 2 of the definition of component because there are additional nodes we could bring in, and we would still have a connected subset. So any smaller group within this bottom portion here is not a component because it's part of the whole collection of nodes that is connected. So we would say in this example, there are exactly 3 components. So here's an example. This graph is taken from that Easley and Kleinberg book, and it's actually a network or graph of high school students at some large American high school where each node represents a person or a student, and each line represents a romantic relationship between one person and another over some 18-month period. So you'll see here that there is a large section of the graph where there are many interconnected components. So one example, you look at this blue node, he's connected to 1, 2, 3, 4, 5, 6, 7, 8, 9 pink nodes. So this particular student, I'm assuming he's male, given this legend down here, was connected to 9 female students over this 18-month period. The question we would ask is how many components are there in this graph? Go ahead and think about that for a minute. And what we'll do in a few seconds is we'll go ahead and count those. So the number of components here is 1 for this large section. So we have 1 component up here. We have a second one, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 different components in this graph. Okay, so this is the last concept that we'll cover in this particular lecture. And we will return here next time and we'll talk about maybe qualitative differences amongst edges in a network. And we'll talk about strong versus weak connections and how that type of classification may be useful or helpful in understanding either why a network looks as it does or how it works.